Alright, so now we're going to discuss edge colorings. So an edge coloring is a function on the edges with the property that distinct edges get distinct colors whenever those edges intersect. So you can't have incident edges that have the same color. And we're going to find the chromatic index, chi prime of G, to be the minimum number of colors in an edge coloring. So a simple lower bound is given by the maximum degree of a graph. Remember, this is close to the upper bound for the chromatic number, but here it's a lower bound, and the reason why is because if you take a vertex of maximum degree, it has to be incident to delta edges, and based on our definition, each of these edges has to get a distinct color. And so this tells you that the chromatic index is at least the maximum degree. However, unlike chromatic number, this ends up being the end of the story because a theorem due to Vizing is that delta G plus 1 is an upper bound. So thus, every graph has chromatic index either the maximum degree or the maximum degree plus 1. And because mathematicians don't have a whole lot of creativity, they refer to these cases as class 0 and class 1. However, before we prove Vizing's theorem, first I want to do the case of bipartite graphs, showing that all bipartite graphs are class 0. So if you have a bipartite graph, its chromatic index is equal to its maximum degree. This also helps us understand some of the background for the proof of Vizing's theorem. So we're going to start with a graph G and an edge coloring C, and a vertex in the graph. We're going to let MCV be this set. So these are what we call the missing colors with respect to the coloring. We take the set of all colors and we remove any color involving an incident edge. So the point is, if I take a vertex V and I look at the colors of the edges incident to V, I remove them from the set of all colors. So if yellow was another option, the set of missing colors consists in this case of just yellow. All right, the other property we need is something called an alpha-beta path. Alpha and beta here are colors. An alpha-beta path in G, starting at vertex X, is a maximal path whose edges alternate between alpha and beta. So this looks very similar to the type of stuff we were doing back when we were studying matchings and graphs. And that actually makes sense, because if you think about it, an independent set of edges is a matching. So an edge coloring is a function on the edges such that each color class is a matching. All right, so we're going to prove the Koenig's theorem for edge coloring bipartite graphs by induction on the number of edges. So we're going to take an edge in the graph. We're going to delete it. By induction, we can assume there is an edge coloring for what's left over, and our goal is to try to extend the coloring if we can. So our first case is that there's a color that is missing at both X and Y. Well, if that color is missing at both X and Y, that means that no edge incident to X or Y has that color. So then you just apply that color to the edge XY, and we know that you're still going to get a proper coloring. So then we have to be in the other case, namely that there is no missing colors in common between these two sets. So we're going to let alpha be a color missing at X and beta be a color missing at Y. And then we're going to define P to be the alpha-beta path starting at Y. So you start at Y, and you start to alternate on alpha-beta edges. Notice here that we know Y has to have an edge incident to it that's colored alpha, because if it didn't, then alpha would be missing at Y and we'd be in case 1. So we have such a path with alternating colors, extended as far as you can go. If it does not end in X, here, then you could swap the colors between red and blue, and then, so if it ended at something other than X, you swap the colors, and then alpha's missing at Y, and you can actually color the graph because you're back in case 1. So we need to assume that this path ends in X. Notice the way I drew this. It ended on a red edge, which is an alpha edge, which shouldn't be possible because of the way we chose alpha and beta. So this picture is also wrong. We have to end down here on an X, on a beta edge. But then you see that the number of red edges and blue edges is the same because we have to start on an alpha edge and end on a beta edge. And that's a bit of a problem because that means you have a path of even length. And so then when we add the edge from X to Y, we have an odd cycle, which contradicts the assumption that we started with a bipartite graph and we deleted an edge from it. And thus we can guarantee that P must not end in X, and we can do the color swapping argument. So now that we've gotten some familiarity with alpha beta paths, we're going to do the full general proof with Vissing's theorem. Since we've already done the version with the bipartite graphs, you already have an idea of how this proof goes. We do proof by induction on the number of edges, so I'm skipping those statements. So we've taken an edge xy from our graph and we're removing it. And so by induction, this smaller subgraph does have a proper edge coloring. And then we continue the same strategy as before. We let alpha be a color that's missing at x and beta be a color that's missing at y. If you can choose these two colors to be the same, then you have a color that's missing at both endpoints of the edge, and we can color that edge with that color, and we now have a proper coloring. So we assume alpha is not equal to beta. As before, if you take the beta alpha path starting from y and it does not end in x, then we can swap colors along that path. And then one of our two colors now becomes available at both endpoints, and we can color our edge as in case 1. Our strategy is going to be dramatically different. The idea is that we're going to be creating a bunch of colorings of G minus X, Y, I for a bunch of different edges of the form X, Y, I, and then trying to find one of these colorings and guaranteeing that we end up in one of these two cases with respect to that coloring instead. And so to start, we have to pick these YIs. This turns out to be the right choice. We're going to let Y1 through YK be a maximal sequence with the following two properties. 1, X is adjacent to YI for all I, and 2, the color of XYI is missing at the coloring for YI minus 1. So in other words, you take some vertex adjacent to X arbitrarily, you look at its color, and you call that other endpoint Y1, and then you ask, is that color missing at any of the other neighbors of X? If so, you call that Y2, and then you look at the color of Y2, and you ask, is that missing at any other vertex? If so, you call that Y3, and then you keep going. And for the rest of the argument, we're going to define Y0 to be the original Y we started with. So the idea is we're going to create a sequence of proper edge colorings of different subgraphs. And so the first coloring is the original coloring we started with. And then we're going to define C sub I to be the ith coloring. And the idea is basically this setup. So here's my original graph coloring. Basically, I'm taking the edge color from X to Y1, and I'm making that the coloring from X to Y0. And I'm leaving the rest of the coloring alone. And then the next color I move blue over. And so the idea is you're sequentially recoloring the graph by making one edge, the ith edge, remain uncolored, and then bumping every color down if we have to. And that's exactly what we see happening here. Then the ith coloring, we let the edge X, Y, I remain uncolored for now. And usually we stick with the original coloring, except for YJ with J less than I, then we bump up the color. And that's exactly what this strategy is doing. Notice that by construction, the color of a given edge was missing at the previous vertex. And so that guarantees that if I move the red over, I get a proper coloring of the graph minus this edge. Because if there was another edge incident here that was colored red, then it wouldn't have been missing to begin with. And of course, X was already incident to a red edge. Similarly, blue is missing at Y1, so I'm free to move the blue color over. And so C sub I is an edge coloring of G minus XYI for all I. And moreover, since I'm just permuting the colors of edges incident to X, the set of missing colors of CI with respect to X is the same as the original coloring with respect to X. So first off, let's look at a missing color in the original coloring with respect to our last vertex, YK. We note that this color has to be missing in all the previous colorings. Why? Because if a color was missing in YK, like say there was no green, then because of the way the colorings work, as you might recall, we keep moving the edges over, but at no point do we mess with any colors of edges incident to Y2 until the very end. And so if green was missing, it's going to continue to remain missing. And at the very end, we just remove the color from this edge entirely. So green would still be missing in that case too. If this beta happens to also be missing in the ith coloring with respect to X, then we are always in case 1 at that point. Because we can keep moving the colors around, mainly we're in case 1 with respect to CK, that is. Because then once you get to CK, you have this uncolored edge, and green is missing at both endpoints, so you can color it green. This means that for some neighbor of X, let's call it W, the ith coloring must assign the color beta to XW. And suppose for now C sub 0 of XW is equal to beta, and W is not one of the vertices in our sequence, then it turns out we could make our sequence 1 bigger by just adding W to it at the very end, because then the color of W is missing at the previous vertex, and you have an incidence relation. And so that tells us C sub 0 XYI has to be beta for some I less than K. In other words, beta has to be used on one of the previous vertices before K. And so we see this color beta, it's used on the edge XYI with respect to the original coloring. Due to how the colors shift, we see it's also that same color and C1 XYI, C2 XYI, up to CI minus 1 XYI. Because in each of those cases, we've only moved colors on edges whose endpoint YJ, J is less than I. On the other hand, once we pass the ith coloring, we've moved the color beta to the edge XYI minus 1. And so in CK, that's the edge that gets colored beta. And this is about where we reach the ending point. So let's take an alpha beta path that starts at YK with respect to our last coloring. If that path does not end in X, we are in case 2 with respect to this coloring. And so then we can swap colors and then color the edge XYK and finish. So we're going to suppose P does not end, we're going to suppose P ends in X. So since alpha was missing at X, we know that this path has to end on an edge colored beta. Of course, due to how we've constructed our colorings, we actually know which edge this is. The edge colored beta in this coloring is XYI minus 1. So then our strategy is to work with the coloring C sub I minus 1 instead, and take the alpha beta path P prime that starts at YI minus 1. So then we look at the edges of P. The edges of P are not changed when we look at these different colorings, CI and CI plus 1. And so we can conclude that YK is on P prime. And since beta happens to be a missing color at that point, vertex, with respect to the I minus first coloring, this tells us that P prime has to end in YK, even though it started at YI minus 1. And so since it does not end at X, we finally find an alternating path And so we're in case 2 again, with respect to this coloring C sub I minus 1. And since this proof tends to be a little bit complicated, let's actually go through it as a quick summary. So this is the idea, is that we've taken a vertex X, we've deleted an edge Y0, we have a graph coloring of the edge coloring of the remaining graph, and then we've found this sequence of vertices with the property that the color appearing on the edge is missing at the previous vertex. And we found a maximum such sequence. And so the point is there has to be a color missing here. Note that the reason why we know that there always has to be a color missing is because there's at most delta edges incident to a vertex, and we have delta plus 1 colors. And so the first part of the argument was showing that this missing color has to appear on one of these edges coming before, say a yi. And so then we have these other new colorings. And so now that we're at the end of the proof, we see these are the only 2 colorings we actually care about. And so the idea is Ci minus 1 is given by having every color before yi jump 1 to the left. So vertex edge xy0 got the same color that xy1 previously had, all the way up to yi minus 1, which is now left uncolored. And the same thing happens in ck, everything jumps 1 to the left. And so the point is this color blue that was missing is still missing here. So if we take a color that's missing at X, like say yellow, and we start looking at a yellow-blue alternating path, if we don't end up at X here, then we can swap the colors and color the remaining edge yellow. So it must be the case that it ends, this yellow-blue alternating path ends in X. Since yellow is missing at X, it ends on a blue edge. And since there's only one such blue edge, we know we must be in a case like this, where it ends on this edge itself. And so then the point is we look at Ci minus 1, and we take the same color path, yellow, blue, yellow. And the point is each of these edges here is not incident to X. So when we're doing this color changing algorithm, we don't change the colors on these edges. So in other words, we must still have this situation here with this path. And in particular, that means it has to end in YK on a yellow edge. And thus we can do the color swapping here and get blue, yellow, blue. And now the color yellow is available for this edge, and we can finish the coloring. And so the point is not that we can extend the original coloring, but up to some sort of shifts, we can eventually find a black edge where we swap colors on one of these alternating paths, and then thus get our final coloring.